back with Tsang.
Hello. Hello, everyone. I am TK Chen, a graduate student in UCSD, working on fire simulation. My advisor is Dusan Keung, and then I also working with Phil Hopkins and Elliot, and also the rest of fire simulation collaboration. And today I'm going to talk about the cosmic ray feedback in the fire simulation, especially how cosmic ray affect the galactic wind in our simulation. Okay, first of all, why cosmic ray is important in galaxy simulation? First, this is very energetic. This is comparable to the thermal energy and the magnetic field energy and also radiation energy in the galactic disk, especially in Milky Way. Second, it's very relativistic and have a very soft equation of state, so that in expansion of the gas particle, it can reduce the energy much more slower than the gas particle. Also, it have a very long decay times, so that it can provide a long-term pressure support in the galaxy for the galaxy. It also have different kinds of fast active propagation mode, for example, diffusion and streaming, so that it can get out to the CGM very quickly and affect those CGM structure. And I think everyone already knows what is fire simulation, but I want to highlight two important things. Is that now we have MXD in the fire simulation and have implemented cosmic ray physics in Gizmo, so that in the future, that in the fire simulation, that we may include also both like this new element into it. In the simulation, we have implemented the two fluid model. It has two pieces of information. One is about the gas, and the other is about the cosmic ray. The cosmic ray mostly come from the shock acceleration from supernova remnants. 10% of the total supernova energy go into the cosmic ray. The rest go into the gas. And then it can have a diffusion, isotropic and anisotropic diffusion, erection, and also streaming through the galaxy. And it also strongly coupled with the gas. The gas will feel extra cosmic ray support, pressure support, and also heating through the hadronic and Coulombic and hadronic heating to the cosmic from the cosmic ray. And we have also implemented one numerical method to accelerate the propagation of cosmic ray, to call two-moment method. We are independently developed this method beyond penhole paper, and it basically turns a diffusion equation into a wave equation, and then we also have a reduced speed of light, so that it have a much longer time step requirement than the diffusion and than the diffusion equation, so that we can run a very high resolution simulation and have very high diffusion coefficient. Our simulation considers two idealized galaxies. One is at SMC masses, another is Milky Way masses. We have considered a bundle of a lot of different kinds of cosmic propagation model from no cosmic ray with magnetic field, with erection only, and then two other magnetic different diffusion coefficient, streaming, and anisotropic diffusion downstairs. And the full models will be the anisotropic diffusion with streaming, with 3 times 10 to the 28. That is observed in our galaxy. Okay. Then, what is the impact of the cosmic ray on star formation? Basically, it suppresses the star formation rates if the cosmic ray propagation is very slow. With a erection of 3 times 10 to the 27 in diffusion coefficient, then we see a factor of tens of percent of suppression of star formation rates in dwarf galaxy and in the Milky Way mass galaxy. But with faster diffusion, then we see the cosmic ray can escape galaxy very quickly, so that it does not make a big impact into the Milky Way disk. Second, it's also very important in driving galactic wind. The reason is that the cosmic ray effectively can decouple with the gas through streaming and diffusion, so that at the outskirts of the galaxy, for example, tens of kiloparsec, it is greater than the thermal energy. And the cosmic ray gradient can be comparable or even larger than the gravitational potential, so that it can drive wind from the center of the galaxy. Here is the gravitational force on the gas compared with the cosmic pressure gradient and the thermal pressure gradient. What we find that it at a very sweet spot of the 3 times 10 to 28 diffusion coefficient, the cosmic ray pressure gradient is comparable to the gravitational force. But with our cosmic diffusion, it's basically the thermal energy supported. So it has to have a very high energy, high temperature. At a higher diffusion coefficient, then the cosmic ray pressure gradient and the thermal pressure gradient is comparable. Okay, here is the shocking image that I have found from in the pressure profile with different cosmic diffusion coefficients. Because we have supernova feedback mechanically coupled to the gas, so that we can drive a very hot winds from the center of the galaxy without cosmic ray or cosmic diffusion. But with cosmic diffusion, that we find that the outflowing wind is move much slower and also much colder. And it may have a very big impact on the CGM. And we should see the 5-day talk that also talk about the cosmic ray effect on CGM. Okay, we quantify it by plotting the outflowing gas particle in terms of the temperature and the sea sea. Then we see when we include cosmic ray feedback, the originally hot phase wind, hot fast moving wind, will become cold and slow accelerating wind driven by cosmic ray gradient, pressure gradient. Although it does make a big impact on the phase structure of the galactic wind, the mass loading factor is quite similar in dwarf galaxy and in Milky Way mass galaxy. We see is around maybe 1 in dwarf galaxy and around 0.1 in LSG galaxy. But for 3 times 10 to 27, because there is a suppression of star formation, so it's a little bit lower in mass loading. Okay, here is my conclusion. And well, I want to highlight that what we have already done, but we haven't covered here, is that we have do a high energy gamma ray emission from the hadronic losses of cosmic ray in fire simulation. We have also simulated the starburst galaxy with high star formation rates and gas surface density, and also we have a cosmological simulation with cosmic ray, but it's only in experiment. That we haven't taken a look at the recycling for here. But the thing is that because the outflow is cooler, but it's also like moving much slower than the normal like mechanical feedback. So it might be take longer time to get back. Yeah.
Can the next speaker come set up? Is there another question? Do you know if the code is significantly slower because of cosmic rays? Do you have a quantification of that?
Yeah, basically in cosmological simulation that we are doing, is like maybe 3 or 4 times lower than the normal ones because of the diffusion and streaming that we are doing. It also depends on the diffusion coefficient that we are going to apply.
Okay, thank you.